Okay, so in this third part of this lecture, we are going to compute the spectral density for symmetric random matrices with Gaussian entries using the replica trick, which is a famous technique developed to study spin glasses and, more in general, disorder systems. Okay, so the quantity we want to compute is the resolvent, which is, as you can see from equation 1, the average over the random matrix ensemble of the trace of the inverse of the matrix plus a diagonal. And an important point is that this function is a complex function with a complex argument z. And so the idea is that we would like to be able to average over the random matrix ensemble. And in order to do this, we are going to use another trick, and which is expressed in equation 2, that actually the trace of the inverse of the matrix can be written as the derivative of the log of the product of the eigenvalues of this matrix, that can be in turn written as the derivative of the log of the determinant. And the idea is that we can express the square root of the determinant as using a Gaussian integral. In particular, we can introduce this variable, these degrees of freedom x, and 1 over the square root of the determinant is just the result of this Gaussian integral in equation 3. So in turn, combining these expressions, what our strategy is going to be to compute the average over the matrix M of this quantity here. So this will be, so what is the form of this term here? As we can see, this quantity z is an exponential of the elements of the matrix M. So in general, if we had to average z directly, that will not be a complicated task, because we will just need to compute the average of the exponential of the elements of the matrix, which is something that is fairly simple if you know the generating function. The reason why this is harder is because we have to compute the average of the log of z. And of course, if you have to compute the average of the log of z, the average is an integral, but you cannot commute the integral of the average with the integral over the degrees of freedom x. So that's why equation 4, it doesn't seem so helpful in solving the problem. And in order to use equation 4, we have to do another trick. And so the replica trick starts from these simple properties of the logarithm, that in general we can write the logarithm as a limit for this n going to 0 of this quantity here. So we can rewrite equation 4 exploiting this quantity and saying that, well, the determinant is just going to be the average of the limit going to 0 of this quantity here. Now, in principle, we cannot exchange in principle, it's not guaranteed that the result is the same if we change the limit with the integration. Let's assume that we can do that, as usually physicists do. And just let's change the limit. There is a long literature when you can do that and when you cannot. But let's say that we change that. So in this case, what we obtain is that actually, instead of averaging the log of z, we have to average z to the n, where n is in principle a real number, and average over m this quantity. Now, again, if n is a real number, this doesn't simplify the things strongly, because it's not easy how to average z to a real number. What we're going to do instead is to assume that n is a natural number, So it's like 1, 2, 3, 4, 5, an arbitrary natural number. And in that case, if n is a natural number, we can write z to the n as a combination of integrals. And then, after we do that for an arbitrary n, we're going to do an analytical continuation of the result and take the limit of n going to 0. So the trick is, let's say that this n, instead of being a real number, is a natural number, an arbitrary natural number. Let's compute everything assuming that is an arbitrary natural number. And then when we have the result, let's take the limit of this natural number going to 0. Let's extend the result to real numbers and take the limit. Okay, so if n, small n, is a natural number, we can write z to the n as a product of integrals. And so then what we can do is that we can introduce on these degrees of freedom another index, indicating this index going from 1 to n. This is usually called a replica index. And then we have this integral. And again, what you can realize is that this integral is again linear. It's an integral of an exponential of m. So now we can average over m, and the quantity we want to compute is this average here, right? And so what you see is that now we basically have exchanged, going from 8 to 9, we have exchanged the order of the integration, and we are averaging over m. So for instance, let's say that the entries of m are, m is a symmetric matrix, and the entries are drawn from a Gaussian distribution with standard deviation sigma over square root of n, and mean 0. The reason why we are taking the variance to be sigma, the standard deviation to be sigma over square root of n, is because we want to have that the final integral will have the right statistical properties when we take the limit of n going to infinity. Okay. Otherwise, if we were not to take this choice here, we would have a sort of trivial limit when we were taking the limit of capital N going to infinity. Okay, so in this equation, in this integral here, we have this term here that we want to integrate. So I just reported this part here, that the part that depends on m. And this is an integral of this type here with which known solution. And so if we put all the results together, we get that this integration here becomes something like this. There is nothing particularly deep here, it's just Gaussian integral. And therefore we obtain that the average of z to the n is this expression here. So this expression is, we have integrating over the randomness of the matrix, and we are left just with the integral over the degrees of freedom. So at this point, we can do some algebra and rewrite the exponent of this, the argument of the exponential of this term that we are integrating in this way here. And we can also define this quantity, which is a matrix within the indices over the replica indices, which is just, it's called overlap, and is just a scalar product over the degrees of freedom. So again, we can introduce in the integration a delta function, basically stating that we are rewriting this expression here in terms of q, and we just plug the delta function here, and we obtain this expression. Okay, so then we can do okay, so let's recap what we've done until now. So what we've done is that we introduced with this replica index, and we have two integrals. We have one integral over the randomness of the matrix and one integral over the degrees of freedom. We integrated over the randomness of the matrix, and we are left with the integral over the degrees of freedom. What we did next is we want to do a change of variables and write this overlap of the degrees of freedoms in terms of new variables that we call capital Q. So we introduce these new variables. At this point, we are left with the expression 16, where there is this delta function. So what we can do is that we can express this delta function as a Fourier integral, introducing a new variable, this variable lambda. And if we put everything together, we see that the only terms that depend on the degrees of freedom x is this term here, linear in lambda. So we can now integrate over x. This integral is something that is similar to a Gaussian integral, but it's integrating over the imaginary axis and is called Fresnel integral. And the result, the value of this integral, it's this quantity here is just the determinant of this matrix lambda. And so putting everything together, we obtain this final expression here, where we have an integral over the matrix Q and the matrix lambda, and of the exponential of a quantity, and this quantity has this expression here. So as we can see from equation 19, the argument of the exponent is linear in capital N. So since we are interested in the asymptotic behavior of random matrices, where we take the limit of capital N going to infinity, we can use the saddle point method. So the idea of the saddle point method is that this integral here will be dominated by the maxima of this quantity in the exponential when n goes to infinity. So what we have to compute are what are the maximum of this expression here, and we get this. Okay, so to compute the maxima, what we have to do is to derive over the q and the lambdas. And so when we derive this quantity over the lambdas, we obtain this expression that is equal to 0. And so setting this equal to 0 and doing some algebra, we obtain that actually this is the relation between lambda and q. And so substituting it in the free energy, we obtain this expression here, right? And this expression here, we have to maximize it over now the only argument that is the matrix Q. And by deriving over Q, this is what we get, right? So this is the second equation that we get. We got this first equation deriving over lambda, and we get this second equation deriving over Q. And this is the equation that we obtain if we write it in matrix form. Now, instead of solving for an arbitrary matrix Q, we introduce an ansatz where the matrix Q has a diagonal term that is equal to Q and the off-diagonal term that is equal to P. This is called replica symmetric ansatz because basically you are only distinguished between diagonal and off-diagonal elements. And if we introduce these ansatz in the equation, we obtain an expression for P and Q. And okay, so there is like some simple algebra to do here, but if you try to maximize this quantity, you obtain that the maximum is obtained when the off-diagonal elements of Q, so when P is equal to 0, and the diagonal elements are equal to this expression here that depends on Z. Okay. So the final result is that this quantity here, S, reads this way, where Q star is this quantity in equation 29. Now, what we have got? So the average of Z to the N is equal to E to the NS, where S is this this quantity that is maximized by Q star. And now to compute the average of the logarithm of Z, we have just to take the limit of small n going to 0 of this expression, right? And as we can see, this expression is linear in small n. So this limit is very simple to take, and the result that we get is simply this expression. Now, to compute the resolvent, we have just to derive by Z, and we have just to take divide everything by capital N. And so again, after some simple calculus, we obtain the following expression for the resolvent. Okay, so we obtain this expression for the resolvent, and we can apply the formula we discussed in the second part to obtain the spectral density. So we just take the imaginary part of this G in the limit of the imaginary part of the argument going to 0. And as you can see, if this argument of the square root is positive, then all this term is real, and so the spectral density is 0. If this argument is negative, the imaginary part is the square root of 4 sigma squared minus z squared. Here there is a minus. And then this is the result. Here there is a typo, there should be a minus. And so these results, what we obtained is is called semicircular law, because if the eigenvalue is larger than 4 sigma squared, then the density is 0. If the eigenvalue is smaller than 4 sigma squared, then 2 sigma, then the spectral density is described by a semicircle. Okay, so with this, we concluded the third part. What we did, just to summarize, what we did here, we expressed the resolvent as a derivative of a determinant, of a log determinant, and in turn, we expressed the log determinant as a Gaussian integral. We discussed that in order to take, and then so at this point, what we wanted to do is to take the average over the randomness of the matrix. But we will need to, in order to do that directly, we will have to average the logarithm of this integral. And so instead of averaging the logarithm of the integral, we decided to introduce this replica trick and express the logarithm as the integral to a real number. We took that this real number to be, we restricted this real number to be an integer. We computed the integral for this arbitrary integer, and then we took the limit of this integer going to 0 by analytical continuation. And in this way, we obtained the resolvent, and then applying the standard formula we discussed in the second part, we obtained the spectral density. Okay.